Hello again and welcome to Fluid Mechanics. In the previous lecture we were looking at the static pressure distribution over a flat surface, and we derived formulas for the magnitude of the net pressure force as well as the center of pressure or the action point. And today we want to move on to the hydrostatic pressure force on submerged objects. So what we have dealt with so far is with the hydrostatic pressure force that is distributed over surfaces, let's say. But now we will still do the same story, except now we want to deal with volumes instead of surface areas. So consider this case of a submerged or partially submerged object. The hydrostatic pressure force will actually result in the Archimedes buoyancy force, which is the density of the surrounding fluid multiplied by the displaced volume multiplied by gravity. So it's the weight of the displaced volume. But where did this come from? And today what we will show is that this actually comes from the pressure distribution. That's why you get the rho g, and we'll see how we get the h from here. So if you look at it, it's rho g, and then we have an h height multiplied by an area, so that gives us the volume. So there isn't much new to worry about. It's the same story but looks different. So let's consider a submerged object, and this is our submerged object. It's in a liquid of density rho, and it's all underneath the surface. And let's consider now an element, a volumetric element of volume dV and height h and area dA. So this elemental volume has a height h and area dA, cross-sectional area. The bottom is submerged under a depth of h bottom, and the top part of the element dV is submerged under a liquid of depth h top. So the difference h bottom minus h top will be equal to just the height of the object that we are looking at. So now we started by saying it's the hydrostatic pressure force. So we want to now evaluate what is what the net hydrostatic pressure force on the elemental volume dV is going to be. So that's easy to do. We're familiar with it now. So we have the pressure on top, and we have the pressure on bottom at the bottom. The pressure at the top multiplied by the area, and it acts perpendicular to that area. The pressure at the bottom is multiplied by the area of the elemental object. So here we're talking about dV, and acts perpendicular and compressive. That's why it's pointing upwards. Anything else? And we also have the weight of the well, we're just looking. So now what we're doing is we're not doing a free body diagram. We're saying we have those pressure, we have this submerged object, and due to submersion it's experiencing pressure. What is that net pressure force? That's what we're asking. We're not trying to do any force balance or anything. We're just trying to evaluate this hydrostatic pressure force. So the pressure that we have at the top is just the rho gh, and same thing, the pressure acting at the bottom. And the difference in pressure is the difference in force. The bottom force and the top force is P bottom minus P top times dA. And then we can substitute for, let's see. We can substitute for the pressure to be with rho gh, and that's what we're doing. Multiplied by dA. We can take the rho g outside, and we get h bottom minus h top, which is the height of the element. So that's what we get, rho g hda, and that's where our hda is our volume. So that's why we get a dV. So the net force, the net pressure force on this elemental volume is just the rho g times this elemental volume. If I want, so now what if I break this object into an infinite number of elements of height h, variable height h, and area d, cross-sectional area dA, then I can, the sum of all those volumes will give me my volume. And I sum up all the forces on them, I sum up all the forces dF, sum up all the volumes, I'm going to get the net force on the object. So that's what we're exactly going to do, sum them up, which means we are going to integrate. So that's the integral. We are just going to, the net force due to the pressure on this submerged object is just the dF over the object itself, the whole of the object. So we integrate dF. So instead of dF, we substitute for rho g dV and change the limits of integration. So we were integrating. So now over the object is now we specify it with the volume because our integrand is dV. So rho fluid times g times dV. The density, if we have constant density and constant gravitational acceleration, they come outside, and then I end up with only dV. So when I integrate dV, I'm just going to get V, and this is the submerged volume, and that's what the Archimedes principle is about. Is that this force we're going to this? What is this force that we found? Is the total pressure force due to the hydrostatic pressure force. And that's equal to the density of the surrounding fluid multiplied by the displaced volume. So it's the weight of the displaced volume by that submerged part of the object. So this is what we set out to do, is to show that this pressure force is what actually gives us the buoyancy. And there's a huge industry, the marine industry, that's based on this simple principle, and it's been based on it for 4,000 years or 5,000 years or so. And where does this force act? It acts on the center of volume of this. So if I were to take only the elemental, if I were to ask you, where does this rho g dV act? It acts on the volume of this elemental volume, so it's halfway. But if I am asking about the force F over the whole object, for the whole object, it's going to act on the center of the volume of this whole submerged volume. So it's going to act here. That's the center of volume. So that's the action point. And now this opens up. So as we said, this is the principle of buoyancy, or the buoyancy force. Is important in the marine industry, and we just want to elaborate just for a few minutes on the concept or on the stability of floating objects, since we're talking about buoyancy, and it demonstrates the concept of action, the concept of the action point of the center of buoyancy. So the center of buoyancy is the action point of buoyancy, so it acts on the center of volume of the submerged volume. So let's consider this oval, this thing, the pink shape, to be a ship. That's a cross section of a ship that's in the ocean. So it's partially submerged, as you can see, and in this position, the weight of the whole thing acts on the center of gravity, and the buoyancy force acts on the center of volume of the submerged volume. So this is the center of buoyancy B. So this is a happy condition. But now imagine this ship is in the sea, so there are waves coming from the left and waves coming from the right. And let's see what happens if a wave comes and hits us in this fashion. And let's see, would it capsize the boat, turn it upside down, and make it fail, or is the boat able to sustain it? So we're making the assumption that we have this disturbance which comes from the wave or from some other source. But let's say it's a wave that pushes us and causes the object to be inclined at an angle delta theta. And now let's look at, we still have the gravity force acting on the center of gravity, and we have the buoyancy force that's acting on the center of buoyancy. And now, since they have shifted in location relative to each other, due to because both of them have to be act vertically upwards all the time, and now the object is inclined. So we get this separation distance between them, which creates a coupling moment. So let's see, what is the coupling moment due to this shift from the buoyancy force action line from the gravity force action line trying to do? Is it trying to help the wave push the object further counterclockwise, or is it trying to resist it? So you'll see it's creating a clockwise moment and it's trying to resist it. So this is we get a restoring moment in this case. So this is a well-designed hydrodynamic stability system where a disturbance gets suppressed and the system goes back to its original location. So now let's look at an unstable system, and in this system the distribution of the volume and the distribution of the weight over inside this ship is not done in a very effective way. So we get the disturbance to make the system incline at an angle delta theta, but let's see what's happening here. We get a separation distance between the action line, the center of gravity and the center of buoyancy, so that creates a coupling moment, and this coupling moment is now counterclockwise in the same because this disturbance tries to rotate the object around its center of gravity, and so I get a coupling moment around also the center of gravity that's in the same direction as the disturbance. So this amplifies the disturbance. So a small disturbance gets amplified in this particular system. So it's not very well designed, and it has a higher risk of capsizing and overturning than the system in Part B. So the location of the center of gravity and the center of buoyancy is something extremely important, and that the captain or skipper of the boat or the ship has to take into consideration at all times. There is personality to every ship, and that's why the captain is intimately aware of the contents of their boat, as well as the distribution, as well as its behavior in terms of stability. So that's just a demonstration of the concepts of center of buoyancy and the center of gravity. Okay, so let's do a couple of problems on chapter 2, which is on the hydrostatic pressure distribution. And let's start with a gate, which is here. We have gate AB. It's problem 261 in our book. It has a mass of 180 kilograms, so that's gate AB, and it's pinned around point A. The width into the page is 1.2 meters, and the distance between A and B, the length of the gate, is 1 meter. The gate rests on a smooth surface B, so we have no friction in this direction, in the horizontal direction. And they ask us, so this gate separates on one side glycerin and on the other side water. So let's see what it does. So when I have no water, the glycerin is pushing on the gate. It's creating a counterclockwise moment. that's trying to keep the gate closed. But now let's say I start adding water here. I will now start getting a counter moment that tries to open the gate, and there would be a critical position where if my water height is above a critical location, I'm going to get the moment due to water beating the moment due to the glycerin around the gate, so the gate is going to start to open, and then we'll start having mixing between water and glycerin. So this is this could be a mixing contraption that will allow you to mix when the ratio of the masses are at a certain predetermined ratio, which is defined by the height h and the height of 2 meters. So the question here is, what should this height h be for the reaction point at B? What is this height h, the water height, for the reaction, the vertical reaction at point B to B0? We've already said that it's frictionless, it's smooth surface, so it's frictionless. So we don't have a horizontal reaction at B. And now they tell us there is no vertical reaction at B. So this is the critical height, which is going to give us beyond which any additional increase in the height of the water is going to open the gate and induce the mixing. All right, so let's see how we can find this height h. So let's look at the gate, because the gate seems to be our important element. Sure, there's the glycerin pressure on one side, the water pressure on the other side. So let's do a free body diagram on that pinned gate. So that's our gate. It has it's 1 meter in length, and its center of gravity is halfway between points A and B. So that's half a meter. L is 1 meter, the length of the gate. The center of gravity of this gate AB is submerged under a height h of glycerin, HCG1. So it's the depth of submersion on the glycerin side. On the water side, it's submerged to a depth of HCG2. And our coordinate system is XY as shown. So let's just zoom on that a little bit more. The gate is inclined at an angle of 60 degrees. So we said here's our center of gravity, and we said we want to do a free body diagram. So let's see what are the forces acting on my gate AB. So at the center of gravity, we get the weight of the gate, mg. So our mass is 180 kilograms. And it acts vertically downwards. So if this is our xy, the gravitational vector points downwards. What other forces do I have? I have reactions at A and reactions at B. But also I have, so before we get there, I have the net force due to pressure on the glycerin side. So let's call that F1. And where is the action point? It acts on the center of pressure for the glycerin side. So let's call it CP1. So that's force 1 acts on center of pressure 1. And then on the water side, we have F2, and it acts on the center of pressure for the water side. The glycerin and water center of pressures, which are the action points, do not have to coincide. They might, but they don't necessarily have to. So that's our F2, and that's the center of pressure for the water side, CP2. Then we have, as we said, reactions at A and B. Before we get there, the distance between CP1 and the center of gravity is YCP1, and the distance between the center of pressure 2 and the center of gravity is YCP2. And the reason why we have CP1 and CP2 located deeper than the center of gravity. Goes back to our formulas that we have found before, but very simply, this force is due. So let's look at the glycerin side. The force on the glycerin side is due to pressure. So what is the pressure at this location? It is the rho gh multiplied by rho g multiplied by this height. So I have pressure acting on this point at point A of this magnitude, which I can compute. Rho glycerin times h A times g, rho gh. That's the pressure at point A. At point B, I expect a higher pressure. It is P at B is the rho of glycerin times G times the 2 meters. So this is my pressure distribution. And I expect, so what we're trying, when we say we're computing F1, we're finding the resultant force. So I have a distributed pressure on this member, on this element, on this gate element, and we are trying to find a net force. And you'll see the net force is going. So how do you get the net force? You integrate. So you'll get the area of the rectangle here. So it's PdA, right? So you get a rectangle and you get a triangle, which is this trapezoid. So but where is it going to act? Is it going to act halfway? No, because you have more pressure towards the bottom. So that's the reason why the center of pressure is always deeper than the center of gravity. And that's what we have shown, what we show in this plot is that it's deeper. So moving on, we then have the reactions at A and B. This is our xy, so this is AX, AY, and BX and BY. But by design of the problem, we have a smooth surface at B, so it's frictionless, so BX is 0. And we're looking at the critical height H, which is by design is going to give us a 0 reaction at point B. So that's what the problem tells you. We have no force at point B. Right, so these are our forces, and the gate AB is under static equilibrium. So which means the forces in the x direction, the summation of forces in the x direction will be 0. And also the summation of forces in the y direction will be 0. And the summation of moments around any point is going to be 0. So the gate is not translating, is not going anywhere in the x direction. It's not accelerating. It's not accelerating in the y direction, and it's not rotating around any point in space. So it is static, and it's a static problem. So all these equalities are true, and we could start by solving the sigma fx or by solving the sigma fy. So let's see what we know and what we don't know. We have the reactions at A. We have two forces, two orthogonal forces, which we don't know. The F1, we can get it easily because we have everything known for the glycerin. But for the water side, we don't know what the height H. We were asked to find it. So we don't know what the magnitude of force F2, which means we also wouldn't know what where the location YCP2 is going to be, because it depends on F2. So if I decide to do sigma fx and sigma fy, I have this force unknown and I have the reaction at A unknown. So I have more unknowns than I need. So one way to go about this is if we pick point A and we do a moment around point A, we automatically get rid of the A and the reaction at point A because the moment arm is 0. So we only get moment around point A from the weight, force F1, force F2, and B, the force at B is identically equal to 0. So if I do the moment at A and it's equal to 0, the only unknown that I have is the F2 and YCP2. So that seems to be a reasonable place to start with. Find the summation of moments at point around point A and of the gate, and equate it to 0. So that's the game plan for this problem. And the moment around point A, well, let's see. Force F1. So it's the force F1. Here's the nice thing. Force F1, because it comes from the pressure force, it's going to be perpendicular on the gate at 90 degrees, and it's going to be pointing towards the gate. So we know the direction and we know the orientation. So force F1 acts at a distance. So here I have missing YCP. So here there is missing YCP1. Sorry about that. YCP1. And I've written it in between absolute values because in the formula YCP1 is going to be negative. So the distance between the force F and point A is just YCP1, this distance, plus the length of the gate divided by 2. So that's L over 2. Then my force F2 has a moment arm around point A, so that's my force multiplied by the moment arm, YCP2 plus the length L over 2. And then I have the weight. The weight I can project it onto onto perpendicular and tangential forces. So I project it into two components, and the tangential force is not going to give me any moment around point A, only the normal force. So that would be the mg cosine theta, the 60 degrees, and I multiply it by L over 2, which is the distance to point A, between the center of gravity and point A. Then we now need to substitute. For F1, if you go back to the formulas from the previous lecture, it is the density of glycerin, ρ1, times the gravitational vector times the depth of the center of gravity in glycerin. So that's the submersion depth. So what this is, rho g hcg1, is just the average pressure on the glycerin side multiplied by the area. So the average pressure is just the pressure at the center of that area. It's a result we derived the previous time, and then we find the force F2 on the water side is the density of water multiplied by the depth of submersion of the center of the area multiplied by the area of the object. And then the YCP is just the formula we had before. Here we have a rectangle, so it's rho g sine of the inclination angle times the IXX divided by the F. There is no A here. Too many typos. Okay, so it's just by the F1. So that's also F1. And same thing for YCP2. Rho 2g sine 60 multiplied by IXX. And what is the IXX? It's a property of the rectangle AB. And as we mentioned before, the HCG1, we can compute it easily for the water side. For the glycerin side, we have this height is L over 2 sine 60, so that's L over 2 and here is 60 sine 60, so it gives us this height, and the whole thing is 2 meters, so 2 meters minus L over 2 sine 60 gives me the HCG for the glycerin side. So it's submerged under 1.5, 1.6 meters of glycerin, and I can get the HCG2 for the water side, but it's still going to remain in terms of H because H is unknown. And for the IXX, the moment of area, it's just the BL cubed over 12. So is the 1.2b or is the 1b? So when we derived the formulas, we picked this as y, and this is the direction y along the surface of the gate, and so BL cubed, so L is in the y direction, so it's the 1 meter is what's being cubed here. BL cubed over 12. So that's for a rectangle. Rectangle of, so here is x axis, and that's the y axis. This is B, and this is the L. So L is along the y-axis. So the moment of inertia is measured in meter to the 4. So let's continue. We have found everything, and now let's just substitute. So here's the picture we have. Right. So here we don't have that typo. So we have the moment around point A. Let's substitute for F1 with rho g HCG. So we get that. So let's just go over it. The density times gravity for glycerin is that much, 12,360. And the height HCG, we found it to be around 1.57 meters. And the area of the gate is 1 meter times 1.2. So that's 1 meter along the gate, and 1.2 meters in depth into the page. So we get also F2. It remains in terms of the height of water H, and we need YCP1 and YCP2. So YCP1, we get it. Yeah, I think there is no A here. I have to double check the formulas. It would be a point around 5 centimeters below the center of gravity, and YCP2 will be in terms of H. So here's what you get in terms of H after substitution. And then the mass of the gate is 180 kilograms, so we get the weight. So then you substitute up in the summation of moments, and you get a height of water H to be 2.5 meters. So you'll see I have 2 meters of glycerin, and I have 2.5 meters of water. And if you check the densities, glycerin is about 1.28 or 1.2, so that's 1.25, and the density of water is around 1. So when you multiply those two, you'll get the same moment. So you can get sort of a quick estimation of what the height is. It's going to be the ratio of the densities would be, and the ratio of the heights. Okay, but I think the point behind this example is to appreciate that there is a pressure distribution on the glycerin side, and remember dP dz is minus rho g. That's the equation that's the only equation we're working with in this chapter, is minus rho g. So the slope at which the pressure, that slope at which the pressure varies with depth of submersion Z depends on ρg. So I have a different slope for the glycerin side because I have a different density than I have for the water side. That's the basic point we're trying to convey in with this example, and then the rest is just using formulas, but using formulas and plugging pieces of information in there that we have all of them. So just make sure you understand the gist of this whole thing is that you have pressure distributions on both sides, and due to this linear pressure distribution, you're going to get the net force acting further down than halfway on a uniform depth into the page of the object. So that's the YCP1 and YCP2, the centers of pressure. Okay, we can do one more problem here, and it would be a problem on the Spar buoy. So this is an example to deal with the buoyancy force. So here's a Spar buoy if you're not familiar with it. If you go on a boat in an urban area where you have crowded boats or it's crowded with boats and marine traffic, you'll get these things sticking out of the water, which you call buoys. So now we'll see how they work. They're just floating markings, or you can have them, or they're of different sorts of marking. So they're floating objects or floating sticks in the water. So what you see is what's on top of the water, but there's definitely things beneath the water. So let's see what it looks like. So here's a typical spar buoy. So here we have a spar buoy made of maple wood, so that's wood, and at the bottom we have a steel ball to move the center of gravity all the way down, so to make it stable. So to keep this thing stable, you want, as we've looked at the stability problem, you want the center of gravity to be lower than the center of buoyancy. So you have wood that floats, and then you have steel that sinks, and the combination of this is going to be something that sinks and floats at the same time. So you have something floating of height h of the wood and the rest of it. So what is underneath the water is much more than what you see above the surface of the water. So here you have some information about the spar buoy. It has a square cross section, 5 centimeter, and the whole length is 3.6 meters. They tell you to find, so if you want this height, now you're designing this spar buoy, if you want this height to be 0.5 meter, what should the added mass of steel at the bottom be? What is the mass of the steel? So that's the whole question. And the solution should be is actually easy. The spar buoy is under static equilibrium. So we'll do a free body diagram for this system under, so it's not a gate, it's the spar buoy. Is under static equilibrium. So that's the buoy. So the summation of forces in the y is 0. So this is our coordinate system y. So what are the forces? So now the question is, what are the forces acting on my spar buoy, which we're taking to analyze. Right. So the first thing is we have the weights. We have the weight of the wood. So where does the weight of the wood act? It acts on the center of the gravity of the wood. So it acts halfway between the two ends of the wooden bar. Right? Then we have the buoyancy force, which acts on the center of the submerged volume. So here's the submerged volume. So it acts halfway between those 2 points. So that's my buoyancy force. Because the wood is lighter than seawater, and that makes the thing float. But the action point for the buoyancy force would be at the center of buoyancy, and then we have the weight of the steel ball that acts at the steel ball. So weight 1, weight F buoyancy, and W2. So the sigma Fy is this weight minus the F buoyancy plus this weight will be equal to 0. And that's what we have here. And then we substitute for the weight. The weight is just, that's the wood. So it's the density of the wood, maple wood, multiplied by the total volume of the maple wood, rho g, times the total volume. The total volume is this whole volume from here all the way to the bottom. So it's the whole 3.6 meters contributes to the total volume. The buoyancy force, however, comes from the density of the surrounding water multiplied by the submerged volume. And the submerged volume is only associated with the 3.1 meters. So the whole thing is 3.6, and the sticking part is half, so we get 3.1. And the weight of the steel, because we were asked for the mass of the steel, we'll just keep it as m steel times g. Let's divide everything by the density of water times g. So here I should make a correction. This is not the density of water, that's seawater, because the density of water and seawater is slightly different. There is 2.5% difference. So this is seawater. So here, correct this to seawater. And I believe I may, so divide by rho g. So here you get the density of the maple wood divided by the density of the water. G cancels out. So as I said, divide by rho g of water. And here I should have the specific gravity of seawater. So here I'm missing too many typos today. 1.025, 1.025. So it should be there. Multiplied by the submerged volume. And then I have the m steel divided by the density of water. So substitute the density, so that's the specific gravity of the maple wood, which is given as 0.6. The specific gravity of seawater, so it's the ratio of the density of seawater to fresh water is 1.025. That's 0.6. And the density of water is 1,000 kilogram per meter cube. So you substitute, so here you get the 0.6 is the specific gravity, that's the volume. Here we should still multiply by 1.025. That's missing, so please pay attention to that. Multiplied by the submerged part, which is only 3.1 meter that we mentioned here, multiplied by the cross-sectional area. And then you get the m steel. And then you find the mass of the ball. So when you correct for this 1.25, it's actually going to be 2.45, around 2.45 kilograms. Okay,